Swayam Prabha. Digital India. Educated India.
Welcome to the course on advanced machining processes. Today we are going to discuss electric discharge machining analysis of RC circuit. The organization of the talk is like introduction, analysis of RC circuit with reference to material removal rate, maximum power delivery to the discharging circuit and surface finish. Then I will deal with some problems related to electric discharge machining process. Now, from the discussion of the last two lectures, here are the various parameters which affect the performance of the electric discharge machining process. Let us just see what are those parameters which we have already discussed in the last two lectures. First one is the voltage supplied across the circuit in general and breakdown voltage of the circuit. Then current that is flowing in the circuit, that is the charging circuit is there, discharging circuit is there, that we will discuss today. Then we are using the pulse power supply in EDM. So, the on time of the power supply as well as the off time both are important, and the on time plus off time makes what is known as cycle time. Electrodes can have either normal polarity, that is where tool is negative, workpiece is positive, or reverse polarity where tool becomes positive and workpiece becomes negative. These are the pulse parameters which affect the process performance, we have already seen. Then comes the fluid medium. We can use the deionized water as the dielectric, but there are various kind of the oils that are used as the dielectric, mainly kerosene is one of them most commonly used. Then there is the electrode, you can use the copper as the electrode material, and when you are using wire EDM as we are going to discuss shortly, then there you can use copper wire as the electrode. Also you can use copper tungsten as the material for the electrode, that is the tool. Copper, graphite or tungsten, they are also used as the material for making the tool or the electrode, and you have to make them in different shapes depending upon what final shape you want on the workpiece. Work material is decided by the designer, and it does not really matter whether it has a low melting point or high melting point. You can use whatever is specified by the designer. Then there are other parameters like ignition delay, which I have mentioned to you. Once the breakdown voltage is reached, then for how long the ignition delay is there, it may be 1 microsecond, 2 microsecond or so, that also affects the performance of the process. And second very important point is the deionization efficiency. Once the off time of the cycle is there, how long it takes to deionize the dielectric, so that the next pulse starts affecting or charging the dielectric. Then there is the arcing open and short circuits, which we have not discussed. Then spark gap variation is another very important point, that is the gap between the tool and the workpiece. It may be in the front gap, it may be in the side gap, and how the servo motor or servo system is going to control this particular gap during the process is also an important point. It will decide what is going to be the total cycle time required for machining or shaping and sizing a component. This is very much dependent on the servo control also. Another important point that we have discussed is the gap contamination. Once the EDM process starts, then you have the reaction products or the debris in the inter-electrode gap, you have the gases evolved during the EDM process due to the highly intensified heat generated in the localized area. So, the dielectric also vaporizes and you have all these gases over there, and once the breakdown voltage is reached, then you have the plasma column. And the flushing efficiency is another very important point which decides the performance of the EDM process. If the process is not highly efficient in flushing out the debris, the reaction products and the used dielectric, then definitely the total cycle time is going to be much larger than the expected one. You can have wire EDM process that we will discuss after this chapter, and then EDM we have already discussed there. Then there is a process called EDS, electrode discharge shrouding process, where you can cut the material in 2 pieces or more than 2 pieces using the spark. Now, how are you going to evaluate the performance of the EDM process or wire EDM process? Then there is the erosion rate or material removal rate, characteristics of the kerf in case of wire EDM process, integrity of the finished surface. This is very important point, because EDM and wire EDM are the thermal processes, that is they are heat dependent processes where material is melted and vaporized due to the heat generated at the point of sparking. So, since the temperature is very high in the localized area, it normally leads to what is known as micro cracks, and micro cracks in the machine component are detrimental to the performance of that particular component. Apart from that, due to the high temperature gradient in the localized area and surrounding area, the thermal residual stresses are created in the machine component. That is another point which one should take into consideration while evaluating the performance of the EDM process. So, this diagram shows us what are the various important parameters in EDM and wire EDM process, and they are also the parameters with the help of which you can evaluate the performance of the EDM process. We have also discussed in the earlier 2 lectures the overcut obtained during EDM process in general and drilling process in particular. So, it is very clearly shown over here that here if you see the diagram on the left side, this is the tool and this is the cavity which has been machined with the help of this, and overcut is clearly shown over here. This tells you that is the radial overcut, that is the gap or the distance in the dimension on one side of the electrode and the machine cavity, and if you take whole of it, then it becomes double if it has the same overcut on both sides. Or the same thing you can see here when there is a cylindrical or circular hole being drilled, then you can clearly see the overcut shown over here, or there can be a trepanning kind of the operation, again you can see the overcut represented by thickness of the material removed. Now, I have mentioned to you just now and in the earlier classes also that there is the on time and off time of the pulse, it may be the voltage pulse. Now, in case of voltage pulse, this represents the on time, that is when the voltage is on, and when there is no power supply it becomes the off time, and you can see clearly that there is a certain width of on time and certain width of off time. The ratio of on time divided by on time plus off time, that is given like this, O n over T O n plus T O f. This tells you the duty cycle, and this is very important. It decides the material removal rate also, and in place of square voltage pulses as shown over here, they can be of other shapes also, which are used for minimizing the tool wear, and accordingly you can decide what is going to be the on time and what is going to be the off time. I have also mentioned to you that for machining any material by EDM process, you need to be electrically conductive. There is a certain minimum electrical conductivity the workpiece material should have, otherwise it cannot be machined by the EDM process. So, you can see here all the materials are divided into three categories. One is the conductor, another is the semiconductor, third is the insulator. Now, in semiconductor also up to a certain point as shown over here, this is the minimum necessary conductivity which any material should have to be machined or processed by EDM process, and you can clearly see here there is a certain value which is represented here in terms of specific electrical conductivity, and many people have been designing the materials so that they can be easily machined by the EDM process. That means, they will have this certain minimum conductivity, because without this minimum conductivity they cannot be shaped and sized by the EDM process and to some extent by the ECM process also. Let us see the analysis of RC circuit and how to calculate material removal rate, how to calculate maximum power delivery to the discharging circuit and surface finish, especially in case of RC circuit. Now, there is in relaxation, this is also known as relaxation circuit, and you have the charging, discharging and sparking, three phases are there, which I will show you in the diagram. So, you can see here V s is the supply voltage which you are supplying across the terminals, V c t condenser voltage at time t, R c is the charging resistance, C is the capacitance and I c t is the current in the charging circuit at time t, and this is well known equation. You can utilize it to calculate the current in the charging circuit I c t, that is given by V c minus V c t over R c, and this is the equation 1. You can clearly see in this particular diagram that there is a supply voltage here, DC supply voltage V 0 or V s, here it is written as V s, and here is the R c, that is the charging resistance, and here is the condenser C, where you can calculate the voltage across the condenser at any time t, and it is represented by V c t. Here it is just written V c. So, you can make it V c t also, and the current flowing in this discharging circuit is given by I d, and in charging circuit is given by I c, and on the other right side you see tool is there which is connected to the negative terminal of the power supply, and workpiece is there connected to the positive terminal of the power supply, and the dielectric fluid is there, and the workpiece is shown plus and tool is shown as negative. Now, here is the charging circuit, this is the discharging circuit, and with the help of this particular equation you can calculate the current I c in the charging circuit. Also, ICT, that is the current in the charging circuit, is given by C dVCT over dt, and since this and this they are equal. So, you can equate these right hand side of both the equation. So, you get dVCT over V 0 minus Vct equal to 1 over RCC into dt, and using this particular equation, integration of both sides of this equation will lead to ln, that is a natural logarithm of V 0 minus Vct equal to minus t over RCC plus k 1, where k 1 is the constant of integration. We integrated the earlier equation given in the earlier slide. Now, to evaluate k 1, that is the constant of integration, use the initial condition Vct will be 0 at time t is equal to 0, and this will result, if you substitute this value in this particular equation, then you will get that k 1 is equal to natural log ln V 0, that V 0 is like this. Then what you can do, you can substitute this value of k 1 over here in the earlier equation, then it will give you Vct is equal to V 0, that is the supply voltage, 1 minus e raised to power minus t over RCC, and this help of this particular equation you can find out the voltage in the charging circuit. From this equation 1 in the earlier slide and this particular equation 2, if you use both these equations, then you can also calculate the current ICT, that is given by V 0 over RC e raised to power minus t over RCC. So, we can calculate the Vct and we can calculate the ICT both. Now, the question arises, power delivered to the discharging circuit, how to calculate that? Then energy delivered to the discharging circuit is given by DEN, that is equal to ICT, that is the current, Vct is the voltage, and dt is the time for which this current is supplied. If we substitute the value of ICT from the previous slide and Vct from the previous slide, then you will get V 0 over RC e raised to power minus t over RCC multiplied by V 0 1 minus e raised to power minus t RCC into dt, that you can obtain from equation 2 and 3. So, this is the value of the ICT, this is the value of the Vct. Now, integration on both sides of this particular equation will result as E n, that is the energy, equal to V 0 square RC minus t e raised to power minus t over tau plus 1 tau over 2 e raised to power minus 2 t over tau plus k 2, where again k 2 is the constant of integration, where tau is the RCC. This tau RCC has been replaced by this tau, or this RCC has been replaced by this tau, and k 2 is a constant of integration, and it is evaluated using again initial conditions, that is energy supplied at time is equal to 0 will be 0. It gives the value of k 2 is equal to tau V 0 square by RCC. This initial condition you substitute in this particular equation, then you will get k 2 is equal to tau V 0 square divided by 2 RC, and this value of k 2 can be placed over here. Then substitute the value of k 2 in the above equation, it will result E n is equal to V 0 square tau over RC multiplied by 1 by 2 plus 1 by 2 e raised to power minus 2 t tau t over tau, minus e raised to power minus t over tau. This, with the help of this particular equation, you can calculate what is the energy supplied. Now, let energy E n be delivered to the discharging circuit. This is discharging circuit is the one where tool and workpiece are connected, they are in the machining zone. Now, during that time let tau c is equal to T, then average power delivered will be given like this, that is P average is equal to, we are dividing it by tau c, E n over tau c, that is the time, that will give you the power, V 0 square over R C x 1 by 2, this you can obtain from here by substituting the value of this 1 by 2 e raised to power minus 2 x minus e raised to power minus x, where x is equal to tau c over tau. This is important substitution. Now, when we have this, now we can find out the condition for maximum power delivered to the discharging circuit, because we are always interested that the power delivered to the discharging circuit should be maximum, so that the spark is having higher energy or and you will get higher material removal rate. So, the condition that we know that for having the maximum power delivery to the discharging circuit, this particular condition should be satisfied, that is d p average over d x is equal to 0, because x is the function or variable over here, that is given over like this, and this you can find out here, x is there and here also. So, the solution of equation 5, when we solve this particular equation, it will give the following relationship, that is x is equal to 1.26. If we solve this equation, we will get this, and this is small x, not capital X, x is equal to 1.26. Now, we can substitute this value of x, substitute it in equation 2 earlier, then we get V c t is equal to V 0 1 minus e raised to power 1.26, and this is equal to 0.72 V 0. That means, discharging voltage should be equal to 72% of the supply voltage to get maximum power delivered to the discharging circuit. This is very important relationship which we are going to use while solving the problems. So, this is the supply voltage V 0, which is also represented sometimes as V s. Now, we are always interested what is going to be the material removal rate, either gram per second or gram per minute or volumetric material removal rate in terms of cubic millimeter per minute or per second. So, from earlier equation 2, machining time T can be evaluated as follows. Now, this is the relationship we already know, V c t is equal to V 0 multiplied by 1 minus e raised to power minus t over R c c. Now, from this equation we can arrive at T is equal to R c c ln natural log of 1 over 1 minus V c t over V 0. Now, if we know the time or cycle time, then from that cycle time we can also calculate the frequency of sparking, that is nothing but frequency of sparking is equal to 1 y over t, and if we substitute the values from here in 1 over t, we will get this particular equation where ln is the natural log. Now, we already know that volumetric material removal rate or material removal rate is directly proportional to the energy of each spark, and that is given by half C V v raised to power 2, that is half C V v square, and multiplied by number of the sparks taking place per second. So, that will give you the material removal rate. So, if you simplify this, you will get MRR is equal to K4, that is the constant of proportionality, CVV square, that is what you get from here, and 1 by RCC 1 over ln 1 over 1 minus BV over V 0, that is what you get. Now, here this 1 by 2 has been included in the constant of proportionality K 4, that is to be taken care of. Otherwise, if you are using it separately, then the value of K 4 will be different. Now, here if you see the diagram, schematic diagram showing the condition for maximum power delivery during the relaxation charging circuit. Now, you can see here, as we saw in the earlier relationship, the maximum power delivery is going to be at x is equal to 1.26, that is over here, and this is occurring at 0.72 as the supply voltage, 0.72 of the supply voltage. So, you can see here that relationship is shown over here, and this is the maximum power delivery. So, MRR now, so this particular equation is very important for calculation of the material removal rate, provided you know the value of supply voltage C, that is the capacitance, RC charging resistance, and constant K 4. Now, it is very clear from this that MRR, material removal rate, is proportional to 1 by RC, that is given over here, inversely proportional to RC, that is charging resistance, and this simply means that if you keep decreasing the value of RC, material removal rate will keep increasing. So, at very low value of RC, you can keep decreasing it, but there is a limit. If you decrease the value of RC beyond that particular limit, then what will happen? Instead of sparking, you will get what is known as arc, or arcing will take place, and we are not interested in arcing in EDM process, because it is harmful for both. It will damage the tool as well as it will damage the workpiece. So, we are interested all the time in sparking in EDM process rather than arcing. So, there is a minimum value of RC that prevents the arcing, and that value of RC or the charging resistance is known as critical resistance, and that critical resistance or that minimum resistance that prevents the arcing is given by under the root L by C, where L is the inductance and C is the capacitance. It is based on the experimental results. People conducted lot of experiments and they found that in fact, R minimum is equal to 30 multiplied by under the root L by C. This is valid for a certain machining conditions and certain tool and workpiece material. Now, suppose you are given the details of the RC circuit as we have seen in the earlier slides. Can we evaluate the surface roughness that you are going to get with the help of that particular EDM process and that RC pulse generator? Now, before that, let us see here, this is the kind of the crater you are going to create if you are giving a given a certain machining conditions. Now, you can clearly see this is the crater, and here no spark has taken place. So, you get unmachined area. H is the depth of the crater and Fc is the frequency of charging. Now, you will get that if frequency of charging changes, you can get this particular type of the crater formation, and they will be close to each other. Quite possible at different frequency or due to the movement of the workpiece in x and y direction, you will get the overlapping craters, and in this overlapping crater you can clearly see that initial is this depth, but when overlapping is there, then this depth reduces substantially, and you have already seen that if you increase the frequency of charging, the surface finish improves, and this is one of the reasons how the surface finish is improving with larger frequency, because the craters get overlapped with each other and their RA value or central line average value keeps decreasing as shown in this particular third one, and here actually the depth of crater is reducing, and that is another reason why you are getting a better surface finish. So, H, capital H, that is the central line average value, is proportional to H, that is the depth of the crater, and F c is the charging frequency, because larger the charging frequency, lower is the value of H, and larger the value of the small h, that is the depth of crater, larger will be the CLA value. Keeping this in mind, volume of material removed will be proportional to H cube, whatever is the height of the crater. If you assume this crater as the hemisphere in the shape, then the volume of the material removed will be proportional, directly proportional to the H cube. So, H cube and this value of H or H cube will depend upon the energy per spark. What is the energy? More the energy, deeper will be the crater, larger will be the value of H. Less the energy, shallower will be the crater, and smaller will be the value of H. So, that we can write H cube is directly proportional to half C V V square. Or you can write down H, that is the depth of the crater, proportional to C multiply C raised to power 1 by 3 and V V raised to power 2 by 3. So, you can write down actually, because from this particular equation now you can write down this equation, H is proportional to C raised to power 1 by 3 V V raised to power 2 by 3 divided by F c, that is the sparking frequency. But we know that F c, that is the frequency of sparking, is proportional to some r raised to power minus m and c raised to power minus n, where m and n are the constants. Using this particular relationship, this equation can be written H is equal to k V V raised to power 2 by 3 c raised to power 1 by 3 plus n and r raised to power m. Now, here again k is the constant of proportionality. You have to evaluate it with the help of the experimental results. However, from different experimental results, it is concluded that H is equal to some constant k 7 or k, it does not matter, V V raised to power 0.5, c raised to power 0.31 to 0.36, that the value of the constant n plus 1 by 3 vary in this particular range, and whatever is this, that is taken care of by the constant. Now, using these particular formulae, I will try to solve some of the problems related to EDM process. Problem 1 is very simple. Let us see it, what it says. EDM is used to machine a metallic sheet. Calculate surface finish value if C, that is the capacitance, is 15 microfarad, breakdown voltage is 130 volt, K 6 constant is 4. Use the equation based on experimental results. Surface finish equation based on experimental results is as follows: HCLA is equal to K 6 V V raised to power 0.5 and C raised to power 0.33. We are already given the value of C over here and V V is given over here. So, you can use these, and K 6 is also given over here. Substitute these values in this particular equation, then you will get HCLA is equal to 4 into 130 raised to power 0.5 and 15 into 10 raised to power minus 6, because this is in microfarad, 10 raised to power minus 6 and 0.33. If you solve this, you will get HCLA is equal to 1.17 micron. Now, let us take the second problem. during electric discharge drilling of a 15 millimeter diameter hole in a plate of 6 millimeter thickness, brass as tool and kerosene as dielectric are used. The resistance and capacitance in the relaxation circuit are 50 ohm and 20 microfarad respectively. The supply voltage is 150 volt and the gap is maintained such that discharge takes place at the condition of maximum power delivery to the discharging circuit. Assume the value of constant K 1 equal to 0.18 to get MRR in cubic millimeter per minute. So, calculate the approximate cycle time. We are given with the following data: hole diameter to be drilled is 10 millimeter, plate thickness 6 millimeter, resistance 50 ohm, capacitance 20 into 10 raised to power minus 6 farad, because it was given in microfarads, supply voltage 150 volt, breakdown voltage of the dielectric, maximum power delivery condition, that is 0.72 into supply voltage, this will come out to be 0.72 into supply voltage is 150. So, you can calculate what is the maximum power delivery condition, and K is 0.18 or K 1 as written in the earlier slide to get MRRV in terms of cubic millimeter per minute. So, what is the volume of material to be removed in drilling this particular hole? That is equal to pi by 4 d square. This gives you the cross sectional area of the hole to be drilled and the plate thickness. Substitute the value of d, that is the 10 millimeter as the diameter of the hole as given over here, and thickness of the plate is given as 6 millimeter over here. So, substitute these values and calculate it, you will get 471 millimeter cube as the volume of the material to be removed during drilling operation. So, now let us see what is the equation for calculation of the volumetric material removal rate in EDM using the RC circuit, that is given by K VV raised to power 2 RC multiplied by 1 over natural log 1 over VV minus V 0. Now, let us substitute the values, because we are given with the value of K as 0.18, VV as given over here 0.72 into 150, RC charging resistance is given as 50 ohm, and supply voltage is already given as 150 volt, either Vs or V 0, both are the same thing. Let us substitute these values in the equation like this over here, and you can find out this natural log of this particular factor. You will get 0.28 over here, and if you simplify this, you get like this. Here this is the K 1 supply voltage square over there, and 0.72 is multiplying factor. So, that you really get VV square from this particular factor. This is the resistance and this is that particular factor. So, you get volumetric material removal rate as 32.985 cubic millimeter per minute. Now, we want to calculate what is the time required for drilling the hole. So, for that purpose, first we should know what is the total volume of the material to be removed while drilling the hole, and what is the volumetric material removal rate of the process. If you divide first by the second one, then you will get the time in terms of minute. So, you will get time required as 14.27 minute, because 471 is the one which was calculated earlier as the volume of material to be removed, and 32.985 is this what we have calculated as volumetric material removal rate. So, you get 14.27 minute as the time required for drilling the hole. Now, we are also interested in knowing what is the cycle time T. So, we already know the equation for calculation of the cycle time T is equal to RCC 1 over ln 1 minus Vv over V0. We already know the value of RCC, V0 and Vv. Substitute the value to get this particular value. This comes out to be 0.785 into 10 raised to power minus 3 second. That is, this is the time required for one cycle. Let us take the next problem, that is the problem 3. During EDM, the charge voltage of the condenser is increased, V1 is equal to x1 micrometer. What should be the surface finish at V2? And V2 is already given here, is equal to 4 V1. Use the relationship based on experimental results and not the theoretical one. Now, these are the 4 options given to you to give the correct answer. One of these will be the correct answer. Let us find out how to solve or how to give the correct answer. The surface finish is given by the formula H K7 BV raised to power 0.5 C raised to power 0.131. Now, H we know is proportional, from this particular equation we can easily see that H is proportional to BV raised to power 0.5, because this factor C and K7 will remain the same in this particular case. Then we can write that H2, that is the CLA value in the second case, or that is with supply voltage V2, and H1 with the supply voltage V1, which become VV raised to VV2 raised to power 0.5 divided by VV1 raised to power 0.5, and we know H1, that is the surface finish in the first case, is x1, that is already given over here in the problem. So, we get VV2 is equal to 4 from this particular, if you substitute the value, you get VV2 is equal to 4 multiplied by VV1. Substitute the value, then you get H2 is equal to x1 multiplied by 4 power 0.5, and this will give you H2 is equal to 2 x1. That means, in second case the surface finish is going to be 2 times x1. This is the RA value, and that means, if RA value is increasing, that simply means the surface finish is deteriorating, and this is quite obvious, because as the voltage is increasing from V1 to V2, surface finish is going to be poorer, and that is what you get, that H2 in second case the CLA value becomes 2 times the CLA value in the first case, that is the V1 voltage. So, it is simple one. So, this becomes so you have to write the answer as A is correct. Now, in the above question, that is the problem 3, in place of changing the charging voltage, that was V1 was changed to V2, frequency is changed from F1 to F2. Frequency of sparking is changed to F2, and F2 is equal to 0.5 F1, that is half of the frequency of F1. What is the new surface finish, or what is the new value of surface roughness, that is RA value? 4 options are given again, 2 x1, 0.5 x1, 4 x1 and 0.25 x1. Let us see what is the correct answer. The surface finish in terms of frequency is given by H is equal to K5 BV raised to power 2 by 3 C raised to power 1 by 3 FC. This is the theoretical equation, and H proportional to 1 by FC. So, we get x2 is equal to x1 FC1 over FC2. From these two equation you can derive this one. Now, we are given with FC1, we are given with FC2, FC2 is given in terms of FC1, FC1 here is nothing but F1, and FC2 here is nothing but F2 given in the problem. So, as mentioned in the previous problem, x1 is surface finish at F1 and x2 is surface finish with FC2, then you get the substitute the value, then you get FC2 is half the value of FC1. This is given over here. Now, if we substitute this particular value, then you will get x2 is equal to 2 x1. That means, when frequency of sparking is decreasing, then surface roughness is becoming poorer. That means, it becomes double of what you get in case of F1. That means, Ra value increases in second case, and that means deterioration of the surface finish, and it is quite obvious, as I have mentioned in the earlier lecture, that as frequency increases, surface finish becomes better. Here frequency is decreasing, so surface finish becomes poorer. Next problem says that during calculation of MRR in electric discharge machining process, supply voltage was used as 60 volt in place of actual supply voltage as 40 volt. What is the ratio of MRR calculated using 40 volt and 60 volt? That is the question mark here. Assume that the condition for maximum power delivery to the discharging circuit is satisfied. 4 options are given: 1.5, the ratio of this MRR, 0.44, 2.27 and none of these. MRR we know is proportional to 1 by 2 CVV square into FC. CVV 1 by 2 CVV square is the energy supplied and FC is the frequency. So, we can see MRR is directly proportional to the VV square, that is the breakdown voltage. Now, and we also know breakdown voltage is 0.72 V0, that is the supply voltage. So, this condition is satisfied. So, VV can be written as 0.72 V0. For maximum power delivery, this condition is satisfied, which is given in the problem. So, MRR really becomes proportional to the supply voltage square. So, MRR at 40 volts and MRR at 60 volts, the ratio of this becomes 40 divided by 60 whole square, and if you simplify it, you get 0.44 as the ratio of material removal rate at 40 volt and material removal rate at 60 volt. Here you can clearly see, as you decrease the voltage, definitely energy contained in each spark is going to reduce, and if energy contained in each spark is going to reduce, then volume of material removed is also going to reduce, and that is quite obvious from here, that at 40 volt the material removal rate becomes 0.44 times of what you get at 60 volt. That is MRR 40 becomes equal to 0.44 into MRR 60. Next problem, in a RC circuit, supplied voltage 100 volt, current is 1 ampere and sparking takes at maximum power delivery condition. The pulse frequency is 10 kilohertz. Find the energy contained in each spark if every discharge gives 2 sparks only. That is the case of multiple spark EDM. Normally, so far whatever we have discussed, we assume that only single spark is taking place in each pulses of voltage, but here it is assumed that 2 sparks take place in each pulse. That means, at 2 places there is a minimum resistance where simultaneous sparking is taking place. In theoretical research, many people have assumed this kind of assumption and they have analyzed the process. However, so far experimental, nobody has been able to prove that more than one spark is taking place at a time. The given data are as follows: current is 1 ampere, frequency is 10 kilohertz, or time becomes 1 over 10,000 seconds cycle time. Voltage VV become 0.72 of V0, that is 100 volts given there. So, it becomes 72 volt, and we know energy is given by V I T, V is the voltage, I is the current, T is the time. So, substitute the value of V I T 72 volts current and time T, you get 72 upon 10,000. So, energy contained in each spark will be equal to E by 2, because there are the 2 spark in each cycle. So, this becomes divided by 2 and you get energy contained in each spark will be 3.6 milliwatt, this is milli. Thus, you can calculate what is going to be the energy contained in each spark. Now, in one of the machining conditions, next problem, frequency of sparking is 8 kilohertz, giving HCLA center line average value RA 1 micrometer. In the second set of machining conditions, only frequency of sparking is changed to 10 kilohertz from 8 kilohertz and all other parameters remain the same. What is the expected surface roughness value? So, we know solution, we know that HCLA inversely proportional to 1 by FC, that is the frequency. So, HCLA 1 over HCLA 2 is equal to FC 2 over FC 1, and we substitute the value of FC 2 and FC 1, then you can get 1 over HCLA 2 10 by 8, and if you simplify you will get HCLA 2 is equal to 0.8 micrometer, that is the surface finish. So, you can see clearly that with 8 kilohertz the surface roughness value is coming 1 micron, and with 10 kilohertz that means frequency is increased, and if frequency is increased then definitely surface finish is going to improve. So, you get 0.8 micron as the surface roughness value. Let us take another problem quickly, that is the problem 8. EDM is being performed under the conditions current and frequency as follows. In one case current is 1 ampere and frequency is 10 kilohertz. In the second case current increases to 2 ampere, but frequency remains the same as 10 kilohertz. In the third case current remains the same, but frequency increases. Very interesting problem. It says make the relative crater size likely to be obtained under the above 3 conditions. So, you can see this is the crater that you are going to get at 1 ampere and 10 kilohertz. Now, in the second case the current increases, but frequency remains the same, it becomes 2 ampere 10 kilohertz. So, now since the current has increased, so you can see the size of the crater that is also going to be larger. Now, in the third case the current remains the same, but frequency is increasing, and we have just seen in the earlier problem that if frequency increases surface finish improves or crater size decreases. So, you can compare this here that with 2 ampere and 12 kilohertz the size of the crater should decrease, and you can clearly see here. That means, it is going to give you a better surface finish. So, this is very interesting to see how the crater size is varying with the change in the current and with the change in the frequency. Last problem, EDM conditions are same under the following cases: use of stratified wire of 0.5 millimeter diameter and use of copper wire of 0.5 millimeter diameter. Comment on the MRR in these 2 cases. Although I have not discussed this stratified wire, I will discuss in the next lecture, but that problem is given over here. The solution says that you will get the same MRR in both the cases. So, this particular problem of stratified wire I will discuss when I discuss wire EDM in the next lecture. So, thank you very much.